Hey folks, how y'all doing? We have a technical and very computational section to cover today. It's on the Gram-Schmidt process. And so I apologize, it's a little dry, but let's go ahead and get started. So over the past couple of classes, we've seen these two theorems here. One of them says that if we have an orthogonal basis for a subspace, then for any vector in the subspace, we can calculate the alternate coordinates of the vector with reference to the orthogonal basis coordinates, just by using this dot product formula. Now, the standard way that we could calculate alternate coordinates is to row reduce. We can always row reduce to find the alternate coordinates. But if my basis is orthogonal, then this is a shortcut. But I can only use this shortcut for an orthogonal basis. And then the theorem that we covered in the last video is that if we have a subspace and a basis, and again, it's an orthogonal basis, then we can project a vector onto that subspace by just projecting the vector onto each individual vector, just calculating the individual vector projections, and then adding them together. And again, this only works if the basis is orthogonal. So with these two theorems in hand that are both useful, the question we might want to ask is then what happens if we have a basis that isn't orthogonal? And the answer to that, and the main idea of what we're covering today, is that any basis can be converted to an orthogonal basis using a process that's called the Gram-Schmidt process. And so what we're going to do is we're going to look and see how the Gram-Schmidt process works. We're going to work through a couple of examples, and then we're going to wrap up. So we're going to start with any linearly independent set of vectors. So it's got to be a basis, so it's got to be linearly independent. And so this is our original basis. And I'm using the letters V to denote the original basis vectors. After we apply the Gram-Schmidt process, we'll have a new basis that's orthogonal. And I'm using W to stand for the new vectors. But these vectors will replace the original vectors because these vectors also span the set V. All right, so the first step in the process, we're going to just take this first vector and just leave it completely unchanged. It is the first replacement vector, W1, is exactly the same as the original first vector. That step's easy. So when I have my V1, let's say we have 4 vectors in our basis. I'm going to just calculate W1 by doing nothing. I'm going to just let V1 be my W1. But here's how we find the other vectors. What I'm going to do is I'm going to project V2 onto W1 using the orthogonal projection formula. And then I'm going to set W2 equal to V2 minus the projection that we just got onto W1. All right, then I'm going to take V2 and I'm going to, V3, and then project it onto both W1 and W2. And I'm going to set W3 equal to V3 minus both projections. Then I'm going to project v4 onto all of the w vectors that came before it. And I'm going to set w4 equal to v4 minus all three of the projections that we have calculated. So the first vector, we don't have to do anything because there's nothing to subtract. But every new vector, we project onto the preceding w vectors and subtract the projections. All right. So let's give this a try. A is this matrix here. We want to find an orthogonal basis for the column space of A. So my original basis, will contain the columns 3, 1, -1, 3, -5, 1, 5, -7, and 1, 1, -2, 8. So these are my original vectors. We'll call them v1, v2, and v3. We're going to build a new basis, the orthogonal basis. And I know that the first vector, my w1, is identical to the original first vector. And from here on out, we have to do some work. All right. So we're going to project v2 onto w1. The projection of v2 onto w1, the formula is the dot product of the two vectors divided by the dot product of w1 with itself times w1 as a vector. So this is coefficient times this vector. So v2 dot with w1 is -15 plus 1 minus 5 minus 21, that's -40. And w1 dot with itself is 9 plus 1 plus +1 plus 9, and that's 20. And w1 is 3, 1, -1, and 3. So we're just taking -2 times this vector. -2 times 3 is -6. Then -2, then +2, then -6. And so W2 is V2 minus the projection. So -5 minus -6 is 1. 1 minus -2 is 3. 5 minus 2 is also 3. -7 minus -6 is -1. So my second vector, my W2, is 1, 3, 3, -1. And now I'll have to find the third vector. So we're going to have to do two projections. We're going to project V3 onto W1 and V3 onto W2. So the formula for this one is V3 dot W1 over W1 dot with itself times W1. And this will be V3 dot W2 over W2 dot with itself times W2. All right, numbers get a little bit messy here. The dot product of V3 and W1 is 3 plus 1 is 4. 4 plus 2 is 6. 6 plus 24 is 30. And the dot product of W1 and W1, we did that over here. It's 20 times W1. And W1 is 3, 1, -1, 3. So 3 halves times 3 is 9 halves. 3 halves times 1 is 3 halves. 3 halves times -1 is 3 halves. and 3 halves times 3 is 9 halves. Then over here, v3.w2, 1 times 1 is 1, 1 times 3 is 3, that makes 4. 4 minus 6 is -2, -2 minus 8 is -10, and w2 dot with itself is 1 plus 9 plus 9 plus 1 is 20, times w2, which is 1, 3, 3, -1. So when we multiply by -1/2, we end up getting, I'm going to put this up here, -1/2, -3/2, -3/2, and +1/2. And so my final answer, W3, is V3 minus both of these projections. I'm abbreviating here, not filling in the details, but 1 minus 9 halves is -7 halves, minus -1/2 is -3. Then 1 minus -3, oh, let's do this one here. 1 minus 3 halves is -1/2. Minus a -3 halves is +2 halves, which is 1 again. -2 minus a -3 halves is 7 halves. 7 halves, no, -2 minus -3 halves is -1/2. -1/2 minus -3 halves is +2 halves, which is 1. 8 minus 9 halves is 7 halves. 7 halves minus 1/2 is 6 halves, which is 3. And so we get -3, +1, +1, 3. And this is our orthogonal basis right here. But this is W3. All right, let's move on to a more complicated example. We want to find an orthonormal basis for the span of these vectors here. So these are my V1, V2, V3, and V4. And our orthogonal basis um, well, W1 is exactly the same as V1. We don't do anything to the first vector yet. So we get -10, 2, -6, 16, and 2. But now we're going to find W2, so we're going to project V2 onto W1. So when we do that, the numbers get a little messy here. We have 13 times -10, that's -130. 1 times 2 is 2. 3 times -6 is -18. -16 times 16 is -256. 1 times 2 is 2. When we add all of that together, we get -400. And then the magnitude of not the magnitude, W1 dot with itself is 100 plus 4 plus 36 plus 256 plus 4. Turns out to be +400 times W1. So, which is -10, 2, -6, 16, and 2. Again, I should have written the formula here. It's V2 dot W1 over W1 dot with itself times W1. Well, this is just -1, so all we're doing is changing the signs, and we get 10 times 10, -2, +6, -16, and -2. All right. But this isn't W2. W2 is V2 minus the projection. So that's going to be 13 minus 10 is 3. 1 minus negative 2 is also 3. 3 minus 6 is negative 3. Negative 16 minus negative 16 is 0. And 1 minus negative 2 is 3. So my next vector, W2, has just a bunch of 3's in it. 3, 3, negative 3, 0, and 3. All right. So now we're going to do the next vector. We're going to project V3 onto both of these vectors. So the projection of V3 onto W1 and the projection of V3 onto W2. So the formula is V3.W1 over W1.W1 times W1 and V3.W2 over W2.W2 times W2. All right. V3.W1 is going to be 7 times negative 10 is negative 70. Negative 5 times 2 is negative 10. 13 times negative 6 is negative 78. Negative 2 times 16 is negative 32. And negative 5 times 2 is negative 10. When we put all of that together, we get um, negative 200. And W1.W1 we did over here, and it's positive 400 times W1, which is negative 10, 2, negative 6, 16, and 2. So this is just minus a half. Negative a half times negative 10 is 5. Negative a half times 2 is negative 1. Negative a half times negative 6 is 3. Negative 8 and positive 1 again. Negative 1, sorry. All right. This projection, V3.W2, 7 times 3 is 21, minus 15, minus 39, minus 15 again is negative 48. And W2 dot with itself is 9 plus 9 plus 9 plus 9, which is 36. Well, this works out nicely because negative 48 over 36 is negative 4/3, and the third and the 3 cancel. And so we end up with negative 4, negative 4, positive 4, 0, and negative 4. W3 is V3 minus these two projections. So we're going to get 7 minus 5 is 2. 2 minus negative 4 is 6. Negative 5 minus negative 1 is negative 4. Negative 4 minus negative 4 is 0. 13 minus 3 is 10. 10 minus 4 is 6. Negative 2 minus negative 8 is 6. 6 minus 0 is 6. And negative 5 minus negative 1 is negative 4. Negative 4 minus negative 4 is 0. And that's our third vector, 6, 0, 6, 6, 0. We still have one more vector to calculate. All right, we're going to do the projection of V4 onto W1. W2, and W3. So the formulas for these are V4.W1 over W1.W1 times W1, V4.W2 over W2.W2 times W2, and V4 times W3, dot product W3, W3.W3 times W3. Let's dig in. V4.W1. So that's negative 11 times negative 10 is 110 plus 6 plus 18 plus 80 minus 14 is 200. V1.V1 we have already done. It's 400 times our first vector W1. So that's negative 10, 2, negative 6, 16, and 2. So that's half of negative 10, half of 2, half of negative 6 is negative 3, half of 16 is 8, and half of 2 is 1. All right. Then this projection, V4.W2, negative 33 plus 9 plus 9 minus 21 is negative 36. And W2 dot with itself is just 9 plus 9 plus 9 plus 9. That's also 36 times W2, which is 3, 3, negative 3, 0, and 3. All right, this just reduces to minus 1. And so when we multiply everything by minus 1, we get negative 3, positive 3, 0, and negative 3. And now we'll do this last projection, make that a fraction. V4.W3. That's negative 66 plus 0 minus 18 plus 30. And that turns out to be negative 54. Sorry. Negative 54 over W3 dot with itself would be 36 plus 36 plus 36 is 108 times V3, which is 6, 0, 6, 6, and 0. Negative 54 over 108 is just negative 1/2. So these change signs and divide by 2. We get negative 3, 0, negative 3, negative 3, and 0. And finally, I'm kind of running out of room here. W4 is V4 minus all of these projections. So that's going to be negative 11 minus negative 5 is negative 6. Minus negative 3 is negative 3. Minus negative 3 is 0. All right. 3 minus 2 is 1. 1 minus 3 is, sorry, wrong row. 3 minus 1 is 2. 3 minus negative, 2 minus negative 3 is 1. And 1 minus 0 is 1. So we get a 1 there. Let me check that again. 3 minus 1 is 2. 2 minus negative 3 is 5. 5 minus 0, that's a 5. All right. Negative 3 minus negative 3 is 0. 0 minus 3 is negative 3. Negative 3 minus negative 3 is 0 again. 5 minus 8 is negative 3. Negative 3 minus 0 is negative 3. Negative 3 minus negative 3 is 0. And then finally, -7 minus 1 is -8. -8 minus -3 is -5. -5 minus 0 is -5. And so that is our fourth vector. 0, 5, 0, 0, -5. But we are not finished with this problem, because this problem asks us for an orthonormal basis, which means they want all of these vectors shrunk down to unit vectors. So to get unit vectors, we have to divide each vector by its magnitude. So the magnitude of this vector is the square root of 10 squared, 2 squared, 6 squared, 16 squared, and 2 squared. That turns out to be exactly 20. So the magnitude of W1 is 20. The magnitude of W2 is the square root of 3 squared plus 3 squared plus 3 squared plus 0 squared plus 3 squared. Well, 9 and 9 and 9 and 9 add up to 36, and the square root of that is 6. So the magnitude of W2 is 6. All right, W3, 6 squared plus 6 squared plus 6 squared is 36 plus 36 plus 36 is 108. Unfortunately, the square root of 108 doesn't work out super nicely. So we'll just leave it as the square root of 8. Sorry, 108. And then finally, 5 and -5 is, when we square that, that's 25, and 25 is 50. So we have to take the square root of 50. All right, so the magnitude of W4 is square root of 50. We will divide each vector by these magnitudes. I have given myself almost no room left, but W1 will be the vector -10 over 20, 2 over 20, -6 over 20, 16 over 20, and 2 over 20. All right, second vector. Divide everything by 6, and so we get a bunch of 1/2s. 1/2, 1/2, -1/2, 0, 1/2. And then these just don't simplify nicely. This is going to be 6 over root 108, 0, 6 over root 108, 6 over root 108, and 0. And the last vector will be divide by root 50, so we get 0, 5 over root 50, 0, 0, and -5 over root 50. And that will be our orthonormal basis. I don't know why I called the whole thing W1. That's a basis. Okay? All right. Let's move on. 2 more examples and we'll wrap up. These 2 are much easier, I think, than the last one because we are looking with a smaller set of vectors. We're going to find an orthonormal basis for this vector, pair of vectors here. So this is my original V2, or V1, and my original V2. So when we build our orthogonal basis, the first vector stays exactly the same. It's 3, -4, and 0. For the other vector, we're going to project V2 onto W1. That's V2 dot W1 over W1 dot with itself times the vector W1. So that's the dot product of these 2 vectors is 3 minus 8 is -5 plus 0 is -5. W1 dot with itself is going to be 9 plus 16 is 25 times W1, which is 3, -4, and 0. So when we multiply these together, this is negative 1/5 times 3 is negative 3/5. Negative 1/5 times 4 is positive 4/5, and 0. But we're not quite done. We want to take V2 minus the projection. So that's 1 minus negative 3/5 is 8/5. 2 minus 4/5 is 6 minus 4 is 2/5. No. 8/5. Hold on, let's see. 10/5 minus 4/5 is 6/5. There we go. And 2 minus 0 is 2. Ah. That's our orthogonal basis, but once again, the problem asks for an orthonormal basis. That's okay. We just divide by the magnitudes of these vectors. This vector has a magnitude of 5. It's part of a 3, 4, 5 triangle, so we get 3/5, negative 4/5, and we get 0. The other one, we're going to have to do a little bit of work here. The magnitude of this vector is the square root of 8/5 squared, which is 64 over 25, 6/5 squared, which is 36 over 25, and 2 squared, which is just 4. And it turns out that works out kind of nice. This is the, let's see, um, 64 plus 36 is 100 over 25. 100 over 25 is 4. 4 plus 4 is 8. That's just the square root of 8. And so we get 8/5 over the root 8. And 6/5 over root 8. And 2 over root 8. All right. For the next problem, we're going to need this basis right here, because we're going to look at the same span, 3, -4, 0, and 1, 2, 2. So that's that span here. These two vectors, they span a plane. That is, these two vectors somehow lie in a plane. And this vector here, 2, -1, 3, doesn't lie in the plane. But the distance from this vector to the plane is the perpendicular distance down here. And we can find that perpendicular distance by first taking the vector that's out to that right angle. And we know the length of that because it's the length of projection. This is the length of the original vector. We can use the Pythagorean theorem to solve for the third side. So here's how we're going to do this. We're going to calculate both projections and add them together. So the projection of V onto, let's use our orthogonal basis. So this is not orthogonal, the orthogonal basis is the first vector stays the same, but the second vector is the one that changes, changes to 8/5, 6/5, and 2. All right. So we're not using this basis, we're using the orthogonal basis instead. The projection of V onto W1 is 2 times 3 is 6, plus 4 is 10. Right? And the dot product of this vector with itself is 9 plus 16, which is 25. So that's 10 over 25 reduces to 2/5. That's 6/5, negative 8/5, and 0. All right. Then we're going to project V onto W2. So that's dot product of 2 and 8/5 is 16/5. Minus 6/5 is 10/5, which is 2. 2 and 6 is 8. Is that right? And then the dot product of V2 with itself is 64 over 25 plus 36 over 25 plus 4. That turns out to be also 8. All right. So 8 over 8 times 8/5, 6/5, and 2. Well, 8 over 8 is 1, so we just get our W2. It's 8 over 5, 6 over 5, and 2. So that's the projection. If we add these together, we get 14/5 and 4/5 and 2. So this is V up here. This is the projection down here. We can use the distance formula to find the distance between them. So that's going to be the square root of 2 minus 14/5 squared, or 14/5 minus 2 squared, either way. Then the next one will be 4/5 minus negative 1. And then the last one is 2 minus 3 squared. All right. So 14/5 minus 2 squared is 16 over 25. 4/5 plus 1 squared, that's 9 on the top. 9 squared is 81 over 25. And 2 minus 3 squared is just 1. All right. So 16 over 25 plus 81 over 25 is 97, plus 25 is the square root of 122 over 25. And so that is our distance. All right. Thank you so much for bearing with me. I will see you at the next video. Y'all take care.